Hello all. So today we start with module 3, that is non-uniform flow. Well, we had already started with non-uniform flow in module 2, the second part of module 2, where we dealt with specific energy and specific energy curve. Okay, so the next part of your non-uniform flow is your hydraulic jump. Now, hydraulic jump, by the word itself, you can understand it is some rise of water. And where does this take place? This generally takes place when you have a barrier in a river or a stream, etc. So what happens? I've taken the example of a dam here. So when I have a barrier, when the water flows down, at this point, the velocity is very high and the depth is very, very shallow depth. It has got high velocity and shallow depth, and it's a very unstable profile. So what happened? It tries to, increase its depth and lower its velocity. So this change from section 1 to 2 is called as your hydraulic jump. Okay, so you have a section 1 where the velocity is very high and the depth is less, and it's an unstable, flow of water, and this is rising to a more stable form of water by increasing its depth and reducing its velocity. So this transition between section 1 and section 2 for a small depth is called as your hydraulic jump. Like as we go further into the module, there are a lot of types of profiles created due to hydraulic jump. So we are just taking a common profile for the derivation part. Now, as I told you, it's a rise of water level which takes place due to a transformation of the unstable shooting. Your shooting is called as a subcritical flow. Your subcritical flow, sorry, not subcritical, supercritical flow. Your supercritical flow is associated with high velocity and depth is low. 2, the stable streaming flow, that is subcritical. Your subcritical flow, your depth is high, your velocity is low. And whenever there is a sudden change of velocity and sudden change of depth, there's a lot of loss of energy taking place. You have a lot of circular motions called as eddies taking place, and generally what happens from section 1 to section 2, there is a quite a significant loss of energy which we'll be calculating in our derivation. Now coming to the expression of conjugate depth of a hydraulic jump. Now conjugate depth, we define it as conjugate depth when we consider the same force at section 1 and 2, and the depth at section 1 and 2 are called as conjugate depth. Now to divide it further, the depth at section 1 is called as initial depth, and the depth at section 2 is called as sequent depth. And both the depths together, when I have the force is same at section 1 and 2, it is called as conjugate depth. Now for the derivation or for the expression of conjugate depth, we have certain assumptions. Okay, we assume that the flow is uniform. When I say the flow is uniform, I mean to say that the discharge is constant. We can't have the velocity constant because you can see very well that the velocity is changing. We can't have the depth also constant. We are just, when I say the flow is uniform, I mean to say the discharge is uniform, and the pressure distribution is due to hydrostatic, pressure before and after the jump. Losses due to friction on the surface of the bed of the channel are small and hence neglected. So since the small length which is happening, your loss due to friction is neglected. Remember that the loss friction due to friction is between two surfaces. Here it is water and your channel bed or sides and bed of the channel, which we are neglecting. And the third thing is the slope of the bed is very small. Okay, remember we give a very small gradient to any channel. And why I'm telling it, assuming it is small is, I'm assuming it is small so that there is no component of weight. See, if I resolve the weight in the x and y direction, there's a small component which causes it to flow. I'm saying that is very negligible. Okay. It's all assumptions. Actually, it has to be counted. For simplifying my equation, I am having, I'm assuming everything is negligible. Now, before I start the derivation, it would be nice that if you have a notebook, and write it down with me. The expression is quite important as far as your VTU is considered. So if you have a notebook, please, solve or, do the derivation along with me. It's slightly a lengthy derivation. Now, this is a typical figure. I've got section 1, high velocity, low depth, and you have a jump And when I have a jump, if there's a rise of water, here the depth is high, your velocity is low. And this is the portion we are considering. From section 1 to section 2, we are considering for the expression of your hydraulic jump. Now, in my derivation, we are considering only rectangular channel sections. Okay, we don't have any other channel section. It's only rectangular. And the discharge we are considering for unit width. If suppose this is my width, let the discharge be 16 meter cube per second, and width is 4 meter. So when I say unit discharge, discharge per unit width, it will become 16 divided by 4, that is equal to 4 meter cube per second by per meter. Okay, for your problems it will be useful. So I just made put a figure of the rectangular channel section, and we'll be denoting discharge by small q. Your small q is discharge per unit width. Okay, so this is my main diagram. So at section 1 and 2 we have hydrostatic pressure on the left hand side and on the right hand side. Okay, so here we'll go to the derivation. Now consider a hydraulic jump formed in a horizontal bed. Consider two sections 1 and 2 before and after the jump. Assume unit width of the channel. Okay. Now at section 1 and 2, let D1 and D2 be the depth of flow. A1 and A2 is the area of flow. Okay. So when I say area of flow, this is my area. Okay, so if suppose my water is till this height edge, the water is never till height edge, just assume if this is height edge, so this base width into this height is my area. So this width I have assumed is as 1, so I have got 1 into its depth. So at section 1 I'll have A1 is equal to 1 into D1. At section 2 I'll have 1 into D2. So that's what I've written it here. Your A1 is equal to 1 into D1. A2 is equal to D2. V1 and V2 are the velocity of flow, and H1 bar and H2 bar are the depth of centroid of area below free surface. Now this you have to recall your fluid mechanics, pressure and its measurement. To be very precise, hydrostatic force on vertical plane. So this is my equation where I make use of your H1 bar and H2 bar. It is basically, see, if this is my area, I'll assume this is my area, width into depth. So for a rectangular area from the free surface, I know the centroid is height divided by 2. So if this is D1, D1 divided by 2 for a rectangular channel. So we have calculated H1 bar, D by 2, D1 by 2, H2 bar, D2 by 2. And this is measured from your free surface, that is your top surface. Your free surface is the top surface of your water in an open channel. And then we are considering discharge per unit width, small q, that is nothing but discharge by B. Your discharge is given as area into velocity by 1. We are assuming it as unit width. And area we got is equal to D, D into V. So this I have written the general equation. So when I have section 1 and 2, I told you the flow is uniform. So I've got Q is equal to D1 into V1, D2 into V2. Please remember this because this equation will be further substituting. I have not put any numbers here. So we'll be further substituting this value. So these are all your considerations. Now here we will be making use of your impulse momentum equation, or more generally momentum equation, which states that the net force acting on the mass of fluid, Fn, is equal to the rate of change of momentum, delta m, and this is used for the derivation of conjugate depth. Now your momentum equation is a slight variation of your second Newton's law of motion. Okay, so my net force is Fn is equal to delta m. So first we'll consider the left hand side. We'll see the calculation of forces. Now here the forces acting are only due to pressure. We have assumed that force due to friction is negligible, and so we are ignoring it. So we are having only forces due to pressure at section 1 and 2. So here pressure force at section 1, F1. I told you the formula is based on your hydrostatic force on vertical surface. It is given by rho g a h1 bar. So a we know it is d1, h1 bar we know it is d1 by 2. So I'll substitute in f1 the value of a and h1 bar. Sorry, here it is a1 and a2. I have just written a. It is actually a1. So A1 will become D1. So when I have it finally, substituted finally, I'll have rho G D1 square by 2. Similarly, pressure force at section 2, F2 is rho G A2. Okay, I have written A1 here, A2 H2 bar. So A2 is D2, H2 bar is D2 by 2. So I'll be getting rho G D2 square by 2. So I'm trying to, convert everything in terms of D2 and D1. My intention is to find a relationship between the depth D1 and D2. Now, when I say pressure force, force due to pressure, pressure force all means the same thing. We are first calculating the pressure and then we are calculating your force from your pressure. Now the net force acting on the mass is given by F2 minus F1. So I'm substituting these value and I can see the common element like, rho G and by 2. So I'm taking it common. So my final expression on the left hand side will become rho G by 2 into D2 square minus D1 square. So this is the left hand side part. And next we will be going to the rate of change of momentum. So if you remember your turbines, the same expressions almost will come. So your delta, rate of change of momentum, is given by mass by time into change in velocity. Now coming to mass by time, mass I always represent it as rho into volume divided by T. Your volume by T is nothing but discharge, so rho into Q. Now since in my expression I'm using discharge per unit width, so what I'm doing, I'm multiplying and dividing by B. Okay, and this Q by B, I'll write it as small q, and we have assumed it as 1, so into 1. So finally my equation will be mass per time will be rho into small q. Now I'll substitute this in this equation, so I'll have rho into q into your change in velocity is v1 minus v2. So what I'm doing, as I told you earlier, we are finding a relationship between d1 and d2. So I want to avoid, whatever other unknowns we have taken. So here what I'm doing is your v1 and v2 I'm writing in terms of d1 and d2. How? I know that small q is equal to v1 d1 is equal to v2 d2. So I'll write v1 in terms of q by d1, v2 in terms of q by d2. So I've substituted this. So again I can take q common, so rho q square d1 minus d2 divided by d1 d2. So this is equation 2. So we know that we are using your impulse momentum equation. So we are equating the force in equal to your rate of change of momentum. So equating 1 and 2, we have rho g by 2 into d2 square minus d1 square is equal to rho q square into d2 minus d1 divided by d1 by d2. Now on this both sides rho will get cancelled. So I'm cancelling rho, and this is d2 square minus d1 square. It is in the form a square minus b square, which I can write it as a plus b into a minus b. So I'm using the same thing. I'm writing d2 plus d1 into d2 minus d1. And here I have taken out rho from both sides. So remaining is q square d2 minus d1 divided by d1 d2. So here I'm cutting d2 minus d1 on both sides. So I'll have, and this g by 2 I'll take it to the right hand side. So I'll have d2 plus d1 is equal to 2q square divided by g d1 d2. Okay, so this is the expression I've got. Now this I'm multiplying the entire this into d2. So when I multiply it, your d2 will become d2 square, your d1 will become d1 d2, and I'm taking this on the left hand side, so it will become minus 2q square into d2 divided by g d1 d2. So my d2 will get cancelled, so I'll have minus 2q square g d1 is equal to 0. Now this, if you see, it's like it's a quadratic equation for your d2. So since it's a quadratic equation, we'll find the roots of the quadratic equation here. So coming to the roots, so it's a quadratic equation of d2. So for ax square plus bx plus c is equal to 0, the solution for x is given by minus b plus minus root of b square minus 4ac divided by 2a. Okay, the solution of this. So similarly, we are trying to find what is the value of d2 here. So we can write d2 in this form and see what are the roots for the equation, what are the values of this equation. So here, if I compare it, I have got a is equal to 1, your b is equal to, b is actually this of constant of x. So here the constant of x is d1, and c is equal to minus 2q square divided by g d1. So I'll substitute all this in this equation. So your d2 is equal to minus d1, that is b, plus minus root of d1 square, that is b square, minus 4 into 1 is your a, into your c value. Your c value is minus 2q square divided by 2g d1. Divided by 2 into a is 1 here. Most of the people forget this part, okay? By 2 part. So that is equal to, so I'm taking this to, to your numerator itself. So what will happen? I can write it as minus d1 by 2 plus minus 2 I have taken inside the root. So when it becomes inside the root, your 2 becomes 2 square inside. So that is equal to 4. So I have root of d1 square by 4 minus 4 into 1 into minus 2q square by gd1 divided by 4. So the 4 and 4 will get cancelled. Your minus and minus will become plus. So if I rewrite it again, I'll have minus d1 by 2 plus minus root of d1 square by 4 plus 2q square gd1. Now there are two values, whenever we have a quadratic equation, there are two values. Now if you see, the first value is minus and minus. Sorry, the second value is minus and minus. We can't have a negative depth. So only my first root is possible, which is minus d1 by 2 plus d1 square by 4 plus 2q square by gd1. Why? Because if I have minus on both sides, it's a negative depth, which is not possible. Okay, so I have only one equation. So this is d2 is equal to minus d1 by 2 plus root of d1 square by 4 plus 2q square g d1. So I can write this q as I told you earlier. Q is equal to v1 d1 is equal to v2 d2. Since all my right hand side is in terms of section 1, I'll be writing in terms of section 1. So I'm substituting q by v1 d1. And see, this is for your problem's sake. My expression ends here. But if suppose your velocity is given, I can use this equation. Minus d1 by 2 plus your entire thing. Okay, and finally the depth of hydraulic jump is given by the difference d2 minus d1. Your d1 is the initial depth, your d2 is a sequent depth, the subsequent depth, sequent depth. And when I'm comparing force, both the depths together are called as conjugate depth. Now I told you about supercritical subcritical flow. Remember one, as I always tell you, super refers to high velocity. Okay, and then the reverse is sub. If you try to remember both, it is always confusing between super and sub. So super is high velocity. Whenever I have got high velocity, the depth is low. Then remembering this, you remember the other part. Okay, so if super is high velocity, sub is low velocity. So with this, I come to the end of my first part of module 3. So tomorrow we'll be doing the derivation for energy loss and expression, another expression for your conjugate depth. Thank you.